Um, okay, so our last talk for today is going to be Bill Rand. You all might know Bill from his course on Complexity Explorer on Introduction to Agent-Based Modeling, or his book with Yuri Lensky on the same topic. So without any further ado, Bill, do you want to get started?
Can you hear me now?
Yeah, I think you're muted there.
Is it still muted? No, you can
No,
hear me?
you're good.
Yeah, okay.
I can hear you now. Go ahead.
Of course, my computer had like a brain fart just as I was starting to bring all this stuff up. So
No worries.
too many windows open. Hopefully, can you see the slides now? Is that good?
Yeah, we can see your slides.
Okay, awesome. So hello everyone, and thank you. And I put myself at the end of the day so as to not to give anyone else that curse of being the last speaker of the day. But I want to, last year when I gave a talk for this workshop, we spent a lot of time talking about biases in big data and agent-based models that might inherit those biases. Still a topic I'm quite passionate about, but I realized last year I didn't get to the second half of that talk. So part of this is going to be the second half of that talk, which is my thinking about different approaches to inverse generative social science. And then specifically in the last couple of months, I found myself working on a project that has to do with generating agent-based models from small data. And so I want to kind of propose how we could do inverse generative society, well, open up the set of questions, let's put it that way, about how inverse generative social science might proceed from small data, or at least medium data in this case. I don't know if it's small, right? It's not n of one, it's n of a couple or n of dozens, right? So let's go from now. Okay, but look, before I do that, let me just talk about one of the differentiations here, right? The beauty of big data, right, and why we like to think about big data is that individuals are leaving their footprints and fingerprints, literal fingerprints in some cases, in the digital sand in a way that we've never seen before, right? These traces represent digital and social signals of human behavior. I've heard some of the people refer to these as digital exhaust, but much like the way that digital, real exhaust is still being emitted by a car moving around, right? Theoretically, it still provides you with some signal of how people are moving and acting in the world, right? And hopefully, there's more information than just that. And we can use these signals to explore the complexity of individuals and discover how they find out about new events, products, services, how they experience the world, how they pass on information to others. A lot of my research focuses around a fundamental question of diffusion of information, right? How do people find things out? What do they do with that information once they have it? And how do they decide to pass that information on to others? But there's a lot of other questions that we ask in this space. Now, interestingly enough, right, a lot of the traditional approaches to big data, I feel like miss the point, right? They essentially aggregate across all the data, which doesn't really seem to be the point, right? Like a sample of big data is just as useful in those contexts as all the data is to a large extent, right? Ignoring sample bias at least, right? And so to that extent, right, really what we want to do is we want to capture the full heterogeneity of the data that we see. And how do we do that? Well, agent-based modeling is one way to do that, right? Agent-based modeling provides a way to understand individual level interactions, right? Now, traditionally, as Josh mentioned and Rob mentioned, right, historically, agent-based models have been rolled your own, right, hand-tuned from the ground up, right? And they haven't been really driven by empirical data. And luckily that's changing thanks to workshops like this one and others, right? But if we could create those ABMs directly from data, we would have individual level detailed models derived directly from digital traces. And if we had the right tools, that would then give us anyone the ability to build an ABM directly from data, right? Wouldn't that be awesome? Like if someone could say, I got this data set, I'm going to set up kind of a rough wireframe of what the agent-based model is. I push a button, all the data gets pulled in and my agent-based model gets generated in a way that exactly corresponds to the data, right? That's kind of the goal and the vision that I'd like to search for. And, this reminds me of the policy flight simulators that were described by both John Holland and John Sturman, two famous Johns, right, who have worked in this space in the past, right? And, in that, the model will then not make actual exact predictions necessarily about where things are going to go, but much like a flight simulator provides you with some insight into, well, if I move the lever up, then I go up, right? The agent-based model flight simulator will hopefully give us a similar insight, right? And let us test the boundaries of what's going on. And of course, like any flight simulator, hopefully gets better over time, right? Apparently, I'm not a big flight simulator flyer myself, but apparently a lot of people spent a lot of time on the Microsoft 2020 flight simulator during the pandemic because it was so ridiculously realistic, right? And it allowed them to engage in their wanderlust even if they were trapped in their houses, right? And so hopefully the same is true with ABM flight simulators. I would argue, and this is not an argument I'm going to make in detail here today, but you can see some of my other works, and I'm happy to talk about it other times, that in all cases, we want the model to be theory interpretable. We should be able to inspect the model and determine how well it relates to theory. We should be able to question, if something goes wrong, we should be able to diagnose and explain why the model is no longer matching reality. And I think that if to do so, to build models without theory is kind of a fool's errand. It can lead us down paths that can be very, very dangerous. And that's something that we spent a lot of time talking about last year. So I'm not going to go into that too much, working on a couple papers in that space, but I won't spend a lot of time there today. So if we have this idea, right, that we want to be able to create agent-based model from data, how do we go about doing that, right? And I would say, that almost all the categories can kind of fall under parameter optimization or rule induction of some sort, right? And parameter optimization is the idea that we construct an ABM based on first principles with unknown parameters. We then take a pre-existing data set and describe a fitness measure to compare model outputs to the data. And then we use whatever optimization tool we want to vary the parameters in such a way that we minimize the difference between the simulated data and the real data. This is essentially what machine learning has been doing for generations. And well, I don't know about generations, a couple of generations, I guess, at this point, but for quite a while, right, to some extent. And we already have tools that can kind of help you with this in the agent-based modeling space. So for instance, in NetLogo, a tool that I worked on for quite a while and still contribute to, we have the behavior search tool that was developed by Forrest Stonedahl. And behavior search essentially allows you to take any kind of fitness function you want to place on your agent-based model, and then it will find the parameters of the agent-based model that best fit that fitness function, right? And so that's kind of a quick example. I'm not going to spend too much time on parameter optimization today, though I do think it's an important concept. I'll spend a little bit of time on it. I'm going to spend a lot more time on the second concept, which is rule induction, which I think is the newest one. So rule induction is the idea that you could use machine learning to extract rules of behavior of individuals from big, and as I will now explain, also small data, right? And construct an ABM automatically from those rules. You can then compare and contrast model outputs to data, refine and repeat. And we've built some tools in the past to help with this. Transcissor is one that I'll mention, but I'm working on a new set of tools that are even simpler to some extent. Transcissor comes out of the Santa Fe Institute it has a relationship to the Santa Fe Institute, I should say, not comes out of it. But the code was originally, the computational algorithms were part of Cosmo Shalizi's dissertation. And we kind of took those and ran with them, and we built a toolkit for that we made available. I think that URL still works, terp/ccb GitHub, but I can provide a different one if that one's not working anymore. Essentially, the goal of Transcissor was give us a time series, and we will generate a Markov-like agent model of that time series, right? It's not a Markov model per se, but it's Markovian in its behavior, and similar to a Markov model in many ways. And then you can embed that agent rule into whatever agent-based model you're using. So just a quick mention about parameter optimization. We have Stone Forest and I have a paper in 2014, which was in the World Congress of Social Simulation, that kind of really formalized this process, and I really like it. And in fact, we're going to be including this formalization in the second edition of our textbook, which should be coming out from MIT Press sometime in about a year, basically. We've signed a contract, we're just in the process of working it. But essentially, if you really want to think about it, you take data from the real world, you split it up into training and testing data. You then have an environment for your training data, environment for your testing data. Now, in many cases, those are the same, but in some they're not. You then have the model and you have a set of parameters. And validation is really about making sure the model matches the real world. Calibration is about adjusting the parameters such that the model matches the real world in such a way, right? And you test that on the tested data using some sort of error function between the output of the model and the testing data that you're observing. A quick example of this that we did that's published in JAS with me and Jeffrey Herman and a couple others. We tried to model information diffusion on Twitter during a couple of hurricanes. So this is Hurricane Irene and Hurricane Sandy. So this goes back a little bit. This is like 2010 and 2012. And we used a diffusion information model called the BAS model, and we used one called the independent cascade model. Each agent was then running this model, and what we varied was whether they got their information from the news, which is the P parameter, versus Q, which is the information from their neighbors, right? And we tried to identify a set of parameters that best optimize, the best match the actual pattern of tweeting behavior that we saw during these runs. And so it's clearly a matter of parameter optimization, a matter of calibration, and you get these nice pretty pictures that show you the places where you get the best feature. In this case, I guess I didn't put the axis up there, but the heat index asset is an error measure. So the bluer, the better. The darker the blue, the better. The higher the red, the worse off you're fitting. And you can kind of identify these spaces where the model is doing pretty well. And as you can expect, there's kind of a trade-off. The model fits pretty well for certain lines that describe the relationship between outside information and internal information. So, the focus in parameter optimization is altering the micro level parameters of the system. The focus in rule induction is identifying macro level, though still individual rules of behavior. So in this case, in some ways, this is a difference of degree, right? Because parameter optimization, if you think about it, each of the rules that an agent is behaving is then being controlled by a set of parameters, right? And so you're just kind of tweaking those parameters. In rule induction, we're saying that the very format of the rules can change, right? So it's kind of going from something like a straight up linear model, right, of what's going on, an additive linear model, if you will, to a generalized linear model where you can have interactions potentially between all of them, and even beyond that, right? Like it may say that there is no linearity at all, right? It might be one of the things that you're breaking in this model, but that's kind of a general idea of how to think about this differently. So it's probably, it's most likely a change in a qualitative change between the two formats, but in the simplest cases of rule induction and the most complex cases of parameter optimization, they can become very similar to each other, right? So in fact, if you have a model where you have, like, say, 3 rules of behavior, and all you're doing is manipulating the probabilities of which of those rules happen, is that rule induction or is that parameter optimization? It's kind of on the borderline, right? So I want to make the argument that these do have similarities, but I do qualitatively think of them differently in my own head, at least, right? So as I mentioned briefly, we used early on in my work, we used the work of Shalazy and Crutchfield to create these Markov-like models. And one of the nice things about these is they apply to a wide range of potential agent-based modeling problems that you might want to face, right? They apply to any system in which you have somewhat high frequency time series data, right? Where there is a limited number of inputs that the agents can take and a limited number of actions they can take. Given that framework, I can infer individual models for 15,000 agents in a fairly fast in computationally efficient time. And I'll show you some examples about that, right? But how can I do this? Well, we're going to assume that the input data series that we're seeing is generated by a conditionally stationary stochastic process. Essentially, that it is a stochastic process. You know, there's a non-determinism to it. However, it's stationary in the sense that, and conditionally stationary, given the past history that I've observed, the probability of me taking a particular action in the next time step is constant over the run of the model, right? Now, it doesn't mean that every time I see the same history, I take the same action. That's not the case. It's a stochastic process, but the distribution over the actions I take remains constant over time, right? Given that, I can then explicitly learn the predictive distribution of the future by grouping together paths that give equivalent predictions. In other words, in a lot of the examples I'm going to talk about whether or not someone is tweeting, for instance, right? And so if I see tweet, don't tweet, tweet, don't tweet, and that gives a 50% probability of tweeting, and I see a tweet, tweet, don't tweet, don't tweet, and that also gives a 50% probability of tweeting, then I group those histories together into the same causal state, is what we call it, right? So we can then create a causal state model for each user using what's known as the causal state splitting and reconstruction algorithm, where we begin with assuming that all the future is always the same no matter what, and then we split off histories as we identify ones that are statistically significantly different from each other. Yeah, I love Cosma's work. I was an office mate with Cosma for a while back in Michigan. And, you know, Cosma is great at proving things, unlike me, where I just go out and make the computer run a bunch of stuff instead. And Cosma was nice enough to prove that this algorithm is both maximally predictive and minimally complex. And we don't mean it in any theoretical sense here. We mean in the presence of the data that we're actually observing, right? So what does that mean? It means maximally predictive in that the algorithm will do the best at predicting the future of any algorithm you could possibly come up with, given the data that's seen, and given that there's no other heuristic bias knowledge that is given to the system, right? So given the past data, it's doing the best possible it can at predicting the future. It's also minimally complex in that the number of states, the number of historical states it will generate, is the smallest number of states that can possibly generate to maintain that maximally predictive property. So we applied this a long time ago with David Darman, Jared Sylvester, and Michelle Gravin to a 15,000 user Twitter base that we were looking at. And we tried to predict whether or not any particular individual would tweet in the future, given the fact that they had how they had tweeted in the last hour and a half, basically, before we made the prediction. And what we are really interested in is, this is a white box model, right? We have an exact model of how these properties relate to each other in the system. What we are curious about was whether or not we could do as well as a black box model, right? A state-of-the-art neural network. In this case, we compared the results to something called the echo state network, right? Which is a recurrent neural network that works very well for these kind of memory-dependent processes, right? Interestingly enough, and small aside, Michelle Gravin has gone on to work with these recurrent networks and reservoir networks in quite a bit. And she actually has some really cool work that I encourage everyone to take a look at, where she shows how if you combine reservoir computing with subject matter expertise, you can create models that are better than either of them independently, right? That they're better than the pure reservoir approaches, and they're better than the subject matter models, right? And so together they work better. That has nothing to do with this talk, but if I highly recommend anyone look at it. It's a great piece of work on social science modeling, right? Anyways, coming back to this work, as you see in front of you, right, what we're showing here is we're showing the improvement of the causal state model, the CSM, over a naive model. And the naive model says that if the person tweeted more than they didn't tweet in the past or tweeted, then they will tweet in the future. And if they didn't tweet more than they tweeted in the last hour and a half, they won't tweet in the future, right? So it turns out that model is fairly hard to beat, right? Like most people follow a pretty constant pattern. And so, you know, trying to analyze their patterns can be difficult. But what this shows is every blue dot here is how much the causal state model was better at predicting than that naive model, right? So right in the middle of the graph, you can see it around a 50% tweet rate. In other words, for individuals who tweeted half the time, we were able to make a significant, almost 70% improvement over the naive model, right? And the echo state network did somewhat similar, but not quite as well. What's the big takeaway from this graph is two things. First of all, the green and the blue dots are pretty overlapping, meaning that we're doing about as good as a pure black box model is at making these predictions, right? The other interesting thing is that for tweet rates in the middle, right, which had the most uncertainty, we did the best at improving the predictive capability of the system, right, which is also useful to know. Just as a cherry-picked example, I have Daniel Zevi here, who is a social media scientist. Try and use examples when I use individual examples to make sure that people are aware that their tweets are public, and I'm hoping this is one. Daniel tweets about 45% of the time, but we were able to predict about 94.7% of the time whether or not they were going to tweet in the next 10 minutes, right? So we do a fairly good job of making that prediction. Just a small aside, we also applied the same role induction principle to loyalty work and loyalty cards for a hotel chain, right? So we looked at customers who were making hotel decisions, and we were able to infer whether or not they were likely to make a hotel reservation based upon the marketing materials that were sent to them, right? And I don't want to get into too much detail, but just to show that, you know, we don't have to just look at this tweet or not tweet option. There's a bunch of others. Now, let me spend the last 10 minutes talking about small data, right? I kind of wanted to get the big overview of parameter optimization versus rule induction. But what about small data? So most of the past examples and most of the examples we've seen today are building agent-based models from thousands to tens of thousands of actions or iterations that happen. But what if you only have a small amount of, I'll call it ethnographic in the standard word sense of the methodology of ethnography, right? You have someone who sits down and records a bunch of things that they observe, right? And what if you have that kind of data? So rule induction may still be possible, but you have to understand how you're going to use that data. You're probably not going to be able to make statistical claims about the outcomes that you would be able to make when you have a larger data set. You will not be able to have the same statistical regularity in 10 observations that you have in 1,000, right? However, this data can be used for more theory exploration and generation and less for theory confirmation, right, is my argument, right? So we can still use this data. So let me give you a specific example. I have data consisting of manually annotated conversations during about 100 surgeries between surgical team members, right? So every single utterance that was uttered during the surgery between any of those team members was marked down and annotated by an expert in the room, an expert recorder in the room, right? Now that person, there was a bunch of HIPAA guidelines they had to undergo in order to get this treatment. So we don't have the exact utterances or anything like that. All we have is who said whom to what, and kind of a variety of tones associated with it, right? Like, was it a command? Was it a query? Was it an informal statement, right? Things like that. So how do we take this data and make an ABM out of it, right? Well, I came up with this idea that we could convert it in the following sense. We're going to first convert the manual annotations to event logs, because ABM and machine learning and all these kinds of things, they like time series data, right? And so I'm going to get a little detailed here, right? And I'm going to talk about what's actually going on. We're going to convert those event logs to probability matrices, right? About what actions the individuals in the surgery are taking. And we're going to convert those probability matrices to event rules, right? And is situated inside of an agent-based model. And now I have an agent-based model of how people behave, and I can run it and simulate it, and I can look at a bunch of different things, right? So to give you a quick, and by the way, I wanted to play around, so I used Google Colab to do a lot of this, and it was working pretty well. It's a nice open kind of Jupyter notebook framework that you can share with other people. So on the left, I have some examples of the data that was manually annotated, right, for a particular surgery. And as you can, basically the way to read this is that the target of the communication is the rows, and the speaker of the communication is the columns, right? So the 23I in the upper left corner is indicating that the circulator said the 23rd utterance informally to the surgeon, right, is how you read this, right? So as you can see, this format's not easily amenable to kind of machine learning in any sense, right? And so I had to think about what to do with it. And so what I did was I first just kind of transcribed it into these event logs where I have each utterance, I have the type of the utterance, I have who the speaker was, and I have who the target was kind of recorded in a file, right? After that, I can then take those event logs, which you can see on the left, and I was thinking about originally I had this great idea. I'm like, oh, I'll create a decision tree out of this, right? Like I'll have a decision tree by which each agent makes a decision. But I decided it was easier and maybe more practical as a first step to build a probability table. So basically, I'm just creating for each agent, if someone says something to me in the last time step, what is the probability that I say something to someone else in the room in the next time step? And eventually I want to take into account, things like the type of communication, whether it's informal, but this is brand new work. In fact, we're probably won't even have this full model up and running to the end of the summer, right? And so I'm still in the process of building all this out. So right now I have this data that basically says if the previous speaker was the circulating nurse and I am the surgeon, then there's about a 25% probability that I will talk to the second scrub tech in the next time period, right? And this is based upon one surgery in this case. I'm hoping we can aggregate over many of these, right, in many respects. So once I have these probability tables, right, I can then create NetLogo code directly from them. And this is kind of the cool part, right? So I can actually output what's called a .nls file in NetLogo, which contains literally this scrap of code right here to set up surgeon, set the probability table, and it has all that. Now, this is not exactly the same as the one I've been displaying for a variety of reasons, but you get the basic idea. And then I write a wrapper script around that basically simulates and says that each time step, call an agent and have them talk. Right. I realize I'm running out of time, so I'm going to kind of get to some of the other questions. So once I have this, right, I can then do things like simulate surgical team combinations that were never seen in the real world, right? I can explore potential interventions on communications. What if you have a surgeon who's been trained to talk more, right? Does that affect the patterns of communications that you can see? And we can examine communication network structures in a more robust and generalizable way. But, this kind of raises a bunch of questions about small data in IGSS. What are the limits to IGSS? Do we need particular formats or kinds of data? I've talked about high frequency data. I've talked about small data. How does the data the model is based on affect the kinds of conclusions that we can draw from the data, right? Does that matter at all? And, ideally, I'd like to start coming up with a handbook of IGSS, right? Can we create statistical tests to help to determine the suitability of input data to create output results for certain goals, right? So if we have a goal of prediction, if we have a goal of hypothesis generation, maybe there's something we can do on the data ahead of time for that aspect. And can we generate a set of best practices for setting up the inverse generative solution? I'll skip to my vision. I think that if IGSS truly takes off and we can make all this happen and we can create these models in kind of this automatic and fully simulated way, I think we are on the way to the policy flight simulator, maybe on the way to something like Asimov's psychohistory from the Foundation series, right? Where we could create these models that are envisioning the future based upon what we've seen in the past. And I think that's really the goal we'd all like to get to in this. So thanks. If you have any questions, we got 1 minute left, but I'm happy to take some questions as well.
Thank you, Bill. Is there any questions?
I have a question.
Go ahead, Christine.
Hey, Bill. Yeah, so as a OR nurse, I can tell you that this is pretty exciting what you're doing with that. Communication is in the operating room is certainly something that could be improved. So I'm enthusiastic about seeing what you're doing. Just a comment, I guess, not a question.
Oh yeah, thanks. Yeah, it was one that I had not thought of originally, but I was approached by somebody who had the data and had this question: could we simulate these communication patterns? And it took some time, but I was like, yeah, I think we can.
Yeah, what you're talking about rings a bell. So I wonder if I've read their work,
Yeah,
perhaps. Yeah.
oh gosh, I can find his name, but he's a professor at Michigan State University, and Nan Nair, who I'm working with on this project. So
Cool.
yeah.
I have a question, Bill. You talked about small data, interesting term. I was wondering, have you thought about how we can address things like sparsity? Like in your matrix, for example, a lot of data points would be missing because just because of the nature of the how the data is being collected. So, have you thought about how sparsity can be addressed? Could that be taken to advantage? Could the agent-based model try to explain some of the uncertainty that comes out of having a sparse matrix like that?
So I have thought about the first half of that question. I hadn't thought about the second half of that question yet, which is how the agent-based model can take advantage of it. From the first half of the question, we definitely did some things to try and limit the sparsity that we have, right? So in some of our teams, we see like multiple surgeons and multiple scrub techs, right? And we basically have decided, well, there is a scrub tech class and a surgeon class, and we're just going to collapse that, because otherwise, trying to model what the second scrub tech is saying when the second scrub tech only shows up in 5% of the surgeries, that seems like that's pushing the limits of the small data aspect, right? But the second question you ask is really interesting, right? Like, could we say something about what the uncertainty? And I think that maybe there is something to be said there, but I don't know the answer. I mean, I'm not a statistician by training, even though I codify statisticians now, right? I feel like there's some way to maybe, given a data that's built on, given an agent-based model, that's built on sparse data, simulate out a whole bunch of runs of that model and say, here are the kinds of distributions of things we'd potentially like to see, right? And given that, then say, well, that's, are the areas where the distributions are wider corresponding to areas where our matrices are more sparse? And if they are, then help to understand that relationship. Maybe say we're less confident about those kinds of things, right? That might be a potential possibility off the top of my head, but I haven't really thought that through.
Yeah, and Christine makes a good point that sometimes the sparsity could have occurred due to nonverbal communication as well. So yeah, there could be multiple factors.
Yeah. I mean, this data set, there are many things I wish, it's a great data set. It's amazing, right? But there are many things as I dig into it that I wish we had more control over at the time, right? So, we're repurposing it for a new use, and it's interesting to see what it comes to. Yvonne, I see you got your hand up.
Yeah, we have
Hi, Bill. Great talk as usual. You mentioned some of or you mentioned what's your vision for IGSS, and Josh did the same at the beginning. So I wonder if either of you can comment about what are the challenges, let's say for the next 10 years. What are the challenges that the community should be thinking or start thinking about if we are to move this field forward?
Well, I mean, one of them I think I highlight a little bit when I talk about the limits of small data, but I also think most of those questions could apply to IGSS in general, right? Which is, I think we need a set of, and this is also true for agent-based modeling to some extent. We need a set of standards, right, and kind of at least best practices, right, about how to apply IGSS, right? I think we need to really foster the community of practice and come up with some methodological guidelines for its use. I think that's the largest challenge, right? To get people to agree on some common terminology and some common agreements. Otherwise, I think you risk the problem that you might become non-cumulative in your knowledge, right? And that's potentially problematic. Josh, you want to add on at all? You're on mute, Josh.
Again, great talk. Thank you for that. I guess I had two thoughts. One is, I do think we should distinguish between the enterprise of explanation and the enterprise of prediction. I think inverse methods can be used on both of those, and I think each of them is exciting, but I would distinguish the two. And in the explanatory interpretation, I think we're looking for, rules, not just probabilities. And to me, one of the ways, and I agree with you completely on data, on standards, on all of that stuff. To me, I think one really important exercise would be to just do some of these for real. I think Yvonne and Chadika have a wonderful one on the Anasazi. Chadika has a really good one on shelling. But I think we should try to pick either some well-known artificial societies and try to invert to get the rules, by which I mean, look around for sugar within your vision. If it's big enough, go there, don't kill anybody, but actual rules. And try to find one there where there really is data, like, contagious financial panic. We have the financial crash. Can we grow that? Can we inverse that data and produce agents that behave that way? They're mass sell-offs. They're a contagious phenomena in public health, in economics, in conflict. I mean, I think, if you say you've got a better mousetrap, you should show some mice. And I think there are all kinds of things we should be doing as a community. Those you mentioned, certainly, but also it would be great to have some real concrete examples of the thing in action. And to me, on the explanatory side, I'd like to see that. And I'm wondering whether things like contagious behavior, vaccine refusal, financial panic, mob behavior aren't good candidates for this sort of work, using the tools you describe and the others that Chadika and others have been pioneering.
Yeah, that sounds great.
Point, Josh. We have another question from Nick.
Yeah, I think this will have to be the last question. We just don't want to run too far over time, but yeah.
Okay, I'll try to make it quick. So you talked about parameter optimization and rule induction, but I wonder if there's kind of like a third category, or maybe you would just put that under rule induction, which is something like topology induction. Like one of the questions that I ask myself a lot is, does spatialization matter in various models? And maybe for your surgery operating room example, where people are standing, does that matter, and how they're going to communicate to each other? I don't know. Is that something we can induce? Is that something we can explore sort of systematically?
Yeah, so I'd be happy to have. I'm curious why you think that would be induction and not optimization, right? Because to me, right, the number of topological locations is only so big, right? And a lot of times, right? Now it may be in many cases it's not, but when I think of induction, I think of we take a large mass of data and we induce a small set of rules that describe that data, right? Is a lot of what I think about, right? Whereas when I think of optimization, right, or parameter optimization in this case, I think of taking a specified set of spaces, iterating over all of the possible spaces, or using some intelligent search to search through that space, and then identifying the one that applies to it, right? And so a lot of times I think of topology, and in fact, when I've done topological work on like social networks, right, we usually approach it more as a kind of optimization problem where we simulate a whole bunch of pre-specified topologies and look at them. But I guess it'd be possible to think of it from an induction standpoint. I'm having a hard time thinking about what that would look like, right? How you would induce relationships in a system. I mean, I guess you could, like in our communication example, right, induce the network of communication, right? But I don't know if that's really that much more than just literally writing out what's in the data, right? It's not clear to me that it's really an inductive process so much as a descriptive process of the data. Right?
I ask that, I mean, I'd like to hear what Patrick had in mind also, if that's okay. If you could still, I think everyone should be free to leave, but I want to stay and hear what Patrick had in mind, if that's okay.
But Nick, that's my thoughts on that, right?
Yeah.
So, so I don't know if you have some different thoughts on that, but that's kind of the way.
So I guess you see it basically as if you can count the number of topologies that you would try, then it's basically a parameter optimization problem. Try all the different parameters.
Yeah, exactly.
And I guess And it's the rule space is much, much larger,
Right.
you would say, in that case. So you're trying to induce that.
Yeah. I mean, this is why I said I kind of had that little caveat that in reality, there may be no difference between these two things, right? Because, Borges, of course, has this great book, our story of the Library of Babel, right? Where it says that all the creative works in the entire world are just, writing down letters in the right order, right? And so really, there is no such thing as creativity. There's just searching for the right words, right? In the right order. And so if you take that mindset, then it's all parameter optimization, right? But in reality, I do think there is, like, qualitatively, I think it's useful to think about a distinction between the two.
So if you don't mind, can we,
no worries.
Patrick, if you're still there.
I've got a sort of silly question followed by what I think is not such a silly point. The silly question is, does your data on operating rooms include the success of the surgery?
Yeah, so we do have outputs of the regarding, there's a number of ways this is measured, like readmission rates and success rates.
That's great, because it may tell you certain patterns of communication optimize successful surgeries.
Yeah.
Or class structure, or the last hierarchical class structure may optimize successful surgery.
Mm-hmm.
The more general point actually goes back to stuff Josh started with at the beginning of the day, which is and has talked about all the way through explanation and as opposed to prediction. I think actually there's a third term that ought to be as part of that, which is normative optimization, where it's closer to explanation in that, and it's not prediction because you're not point predicting, but you may be trying to optimize a communication network. You may be trying to optimize a vaccination network. You may be trying to optimize either structures or sets of rules toward a desirable goal, like Scott was talking about. And in that case, your model, you may be after explanation, but the explanation that you want for a particular purpose. Namely, you want to understand how the mechanism works so that you can make it work better. So I'd say that, the model and goals include, yes, explanation, not point prediction, but yes, some kind of social optimization toward desired end.
Yeah, so would you put that under, Patrick, would you put that under the space of maybe like, I don't want to, I sometimes think of this as education or persuasion, right, with a particular goal or outcome?
No, not necessarily.
Okay.
We may not need to educate anybody. We want to have more successful surgeries, for example.
Right.
So it's not persuading people to get them. It's finding out how we get them. And our model may be able to tell us that by helping us, not by being able to predict Tuesday's surgery is going to be successful.
Gotcha.
But it may be able to tell us, yes, you ought to structure your teams in this way so as to optimize results.
Right. So you're talking about more of like trying to look at what kinds of interventions, for instance, might affect the outcomes to make them more successful.
Yeah, among others. Yeah, that's what you're mean.
Among other
Right.
possible.
Right. Yeah, I agree with that, Patrick. That's a very nice distinction. Very important.
So we have a couple of questions on chat. I don't know if you want to answer them offline, Bill, or
Sure, I can take it. Well, we can. I do think that we should allow everyone to go, and so let me make a quick comment that we will be reconvening at 9:30 in the morning, right? With a kickoff by Yvonne Gerbe, who will be presenting, right, Yvonne? So you'll be there, then we have a series of talks with the keynote by Matthew Jackson at 1:45 in the afternoon. And we'll also be having a discussion. We do want this to be an open-ended kind of workshop where there is considerable discussion around what is going on here. So we have 2 discussion points scheduled throughout the time. One of them is tomorrow, and that will be led by Matt Kohler. I'm just pulling up the time. At at 1 o'clock, just before the keynote presentation, right? And then we will be hosting another discussion at the close of the workshop that'll be led by me at noon on Thursday, right? So the one on Thursday will specifically be about trying to figure out what next steps are. I can hang out for a little bit and answer some questions, but we should probably at least stop the recording at this point and go from there. So thank you everybody for a great first day. Hopefully you'll see a MailChimp email rather than a Google Groups email tonight that will actually get to everybody with highlights of what's going on tomorrow. Take care, everybody.
Thank you all. Thanks all very much.
Thank you all. Bye-bye.
Thanks.
I'll hang around too.
I don't know who's controlling the recording, if it's